Can I get like extra credit if I like rate the camera for all the passes? Like a free pass on the final. I'll take that. Yeah.
I'll help him.
I'll see.
Okay, good morning everyone. Welcome back. You're rested, relaxed, rejuvenated, invigorated. Okay. So, home straight. Just 2 weeks left. A few housekeeping things and quick overview of today and Thursday briefly. And we're going to jump right back into wrapping up on fluid dynamics. Okay, so I continued to ponder this question of the second problem on the second midterm. As you'll recall, this was the revolving rod that had this particle ejected from it. And I told you when we looked back over the second midterm that a few of you, 5 to 10% I think, wanted to use energy conservation on that second problem. It doesn't work if you think about it, and I think all of you did right afterwards. Energy conservation isn't relevant. But having pondered this a bit more and having looked at a couple of scripts, I'm going to kind of give those of you who this impacted, I'm going to give you a small number of points for that second problem if you showed that you understood how to use energy conservation in that problem, even though it wasn't relevant. All right? So, if this impacted you, and I'll send this out over CourseWorks as well so everyone sees it, just bring your midterm 2 script to class as soon as you can, ideally on Thursday. I'll collect it and quickly review it over the weekend and then hand it back. Okay? So that's that second problem on the second midterm. For schedules this week, mostly on the standard schedule with one exception. I'm not available for office hour this afternoon, so please don't come this afternoon. But to make up for that, I will add an hour tomorrow morning, so I'll be in my office also from 10 to 11 tomorrow. We're back on the regular schedule for recitations this week and hopefully next week. So please continue going to recitation and it'll be running in the usual way. Yeah.
We also have to be 5.
Yeah, tomorrow's normal time. Lastly, some of you were scheduled to join me for lunch a few weeks back. The people who helped organize that got a little bit confused, and it was the week when Faculty House was in fact closed. So I rescheduled it for this Thursday. My sense is there are probably a few available spaces if anyone hasn't been to lunch or would like to, and you're available on Thursday this week. Between 1 and 2, shoot me a quick email and hopefully we can add you if you're interested. And for those of you who are signed up for that, I'll send out a reminder probably on Wednesday. Okay. Questions about any aspect of the course as we kind of enter the last couple of weeks? Okay, so we're going to wrap up on fluid motion today. A fairly quick overview of the important aspects of fluid motion. So I want to come back and just talk a little bit more about fluids in motion, fluid dynamics. We saw some fun demonstrations at the end of class a week ago, but I want to go back and look at those a bit more carefully. I also want to give you a couple of sort of standard tips that turn out to be kind of relevant for a large number of problems using the Bernoulli principle. And I'm actually going to work through one problem with you in class on that. And then we're pretty much done. I will say as a footnote, there are a couple of pages of my notes, and I think that's also true in the textbook, on more real aspects of fluid flows, including viscosity and sort of frictional forces. I'm not going to cover it in class. I'm not going to ask you to know that material for any test. But if any of you are likely to be doing anything in your futures that involve a bit more realistic approaches to fluids, you might want to look at that. So I'm going to post those couple of pages of notes, and it's entirely optional. It's up to you. Then we're going to turn our attention to gravitation for today and Thursday. Today will be sort of classical Newtonian gravitation. Some of you will have seen a fair amount of this already. What I'd like to do on Thursday is kind of deviate a little bit from the textbook and start talking about aspects of gravitation that are more contemporary, namely general relativity and some sort of recent questions about gravity that are kind of interesting and maybe surprising. So that'll be a little bit of a kind of just a kind of FYI kind of session, but hopefully you'll find it interesting. Courses like this, intro physics, they tend to be very much classical physics that we've known for a good amount of time. And I wanted to throw in both on Thursday this week and next week when we go to special relativity, some things that are a little bit more contemporary and sort of relevant to the current research. So, in terms of today, Newtonian gravitation, we'll talk about the Newtonian gravitational force. We'll fairly quickly extend that to the idea of gravitational potential energy. We've already seen this in the case of near-Earth gravitation, but we're going to extend this to gravitation over larger scales. We'll talk briefly about Kepler's laws, very much a manifestation of Newtonian gravitation, but sort of a little bit more empirical in what they're describing, and in particular describing motions of planets and moons around central objects. We'll talk a little bit about orbits, and at that point we're going to run out of time. So that's roughly what I was hoping to get through today. Okay, so let's wind the clock back to last Tuesday. Energy conservation in flowing fluids. And I didn't derive this in class. I'm hoping all of you have taken the time to look at that derivation from the textbook or from my notes. But it is simply energy conservation. Okay? So it's a nice way of going back and using what you've learned about energy conservation to a flowing fluid stream. And this is what drops out. Okay? So what it tells us is if we have certain assumptions about our fluid flow, it's incompressible, it's not leaky, it's not kind of rotating on itself, kind of whirlpool-like patterns. With those simplifications in mind, this is what drops out. So what is it relating? Anywhere in a fluid flow stream, we can relate the local pressure in the stream, the sort of height or y position with respect to local gravity, h, and the local fluid flow velocity. Okay, these are hard things to say. Fluid flow velocity. So we're going to exploit that a little bit more. I just want to go back and quickly talk about a couple of the demonstrations we saw last Tuesday to make sure that you understand why what you saw happened. Okay, so we had this kind of fun competition of seeing who could inflate this rolled up plastic bag the most. And what you saw is a perfectly normal kind of response to a situation like this. Your inclination probably is to try and just make a seal around your lips with this and blow as hard as you can into this thing. But somebody who has maybe seen this before or been thinking more deeply about the Nuri principle recognized that there was perhaps another way, a more efficient way to inflate this thing. And somewhat surprisingly, it involves not actually making a sealed contact between these things, but doing this. So what's going on there, and why does that kind of help you inflate that plastic bag? So this has, of course, to do with the Nuri principle. Why does it work to actually not have a seal? This. A little better this time. So why does that work? What does it have to do with this? Yeah?
Is it because the local pressure is lower, so the velocity has to be higher?
Okay. Sort of interesting connection of observables. I'm going to not comment on it just yet to see if anyone else has any thoughts about what's going on there. So keep in mind that what's driving this process is me kind of blowing a stream of air. And what I want you to think about as you try and ponder how this inflates this back so effectively is, what does that tell you? And it's kind of what you said, but it's flipped order. What does that tell you about something else we're doing? So what is it that makes it easy for me to inflate the bag this way?
Me?
Yep.
Does it have something to do with like the pressure? Because pressure is force over area, so it's like you're applying a force which causes it to like push it open or something.
And well, you're also, it's a lower velocity that you're flowing into it in that case. You're accelerating the air around your out into it, so you have a larger area that's then acting.
So let me, because a couple of you have kind of mentioned this in ways that I just want to probe a little bit. Higher pressure. If I had a region of higher pressure, well, first off, where do you want to tell me there's higher pressure? Okay. Maybe there's obviously some air flowing into there. Maybe there's sort of a slight overpressure. Let's keep exploring this. Yeah.
Because of the airflow inside the bag, there's an area of lower pressure in there, and then the air from outside will enter.
Okay. So this is actually getting closer to what's actually happening. So what you can imagine, here's the kind of opening to this plastic bag, like this. And I'm blowing an airstream into here. Now, compare the velocity of this airstream with the velocity of the air that's a little bit outside here, where it's normally at rest, at least overall it's at rest. So I've got air flowing here, so it's got some velocity, which is finite compared to the zero velocity on average outside. So if I've got a fluid flowing in this region that has a velocity, a non-zero velocity, what does that tell you if I'm operating at the same height? This thing is roughly speaking horizontal, so this term drops out. If I've got air flowing at high velocity, what does it tell you about the local pressure in that area compared to a region where I've got an overall velocity flow? Yeah, it's lower. So interestingly enough, right here, the pressure is actually lower than it is out here. So this pressure is lower than it is here. So what's going to happen if I've got a region of low pressure here compared to the ambient atmosphere out here? So the higher pressure air out here is going to try and move into this area of lower pressure. So what's happening, maybe a little bit paradoxically, because you're kind of inclined to think that you're applying some higher pressure in here. Maybe that's slightly true, but what's actually interesting is what's happening in the mouth of this plastic bag. So you're creating a lower pressure region here simply by virtue of making the air flow. And then what's happening is the air from the nearby sort of stationary atmosphere, which is at somewhat higher pressure, kind of rushes in to fill that low pressure void. So this has the interesting effect of kind of, in a sense, pulling in a fair amount of air from nearby, simply because you're creating this low pressure area. So it's sort of this rush of air in that actually helps you inflate this bag in the way that you saw. So it's a kind of interesting demonstration, not immediately what you would expect, I think, but once you've kind of looked at it in this way, hopefully it makes sense, and now you've kind of learned the useful part of creating to inflate plastic bags. All right, other thing that I showed you right at the end of Tuesday's class was this. Fun ball in airstream. If I can get it first time today. So what's happening? What is it that allows that ping pong ball to kind of remain in equilibrium? So you see it's oscillating a little bit side to side, but what is it that allows me to suspend that in a way that you see? Again, think about the Nui. Yeah.
Well, the air below, or directly below the ball is in a lower pressure because it's simply flowing upwards. So, what if the air around it, kind of like the same thing as the bag, but what if the air around kind of into it, below the ball, and keep the ball suspended?
Okay. Okay. I'm okay with that. What about the kind of, as you see, there's a sort of instability here. You would expect in general that if you're pushing something upwards like this, it wouldn't be difficult to apply a force asymmetrically, I mean left-right asymmetrically, in such a way that you would simply push it off one side. So in particular, what gives it that sort of horizontal stability? Yeah.
Is the air around it being sucked into the low pressure?
So certainly we've got air flowing around here, of course, there's an obstacle in the way. I kind of like what you said, just kind of elaborate a little bit for me here. Just try and describe it slightly more precisely. I know it's not easy in words, but what is the airflow and the pressure, what's it doing sideways here?
Is there air from the outside traveling towards it? Sort of?
Kind of, yeah. So think about, again, it's a little bit the same situation here. If I compare the airflow here, it's obviously moving with some speed compared to here. So indeed, there's kind of a sort of pressure exerted in this direction and a pressure exerted in this direction. And if you think about it, if this thing kind of tends to go off equilibrium, tends to move more to one side, what you'll see is this kind of, we need to look at the sort of balance of flow streams here, and you'll sort of see that it kind of compensates in such a way that it's always going to push back to try and keep it in that equilibrium position. So that's a kind of fun way of suspending a ball in an airstream, and I'm just going to show you one variation on the theme here, sort of similar ideas. Upturned funnel, connected to a piece of rubber tubing. Taken my ping pong ball, and I'm just going to stick it in the mouth of this upturned funnel. And if I let this thing go, probably you're going to predict this is going to fall out. Fine. But this one is fun too. I'm going to do this with airflow. What's going on there? Yeah. So again, hard things to describe in words. It's much easier to draw in pictures. So I've got air flowing down here. What can you tell me about the relative pressure in sort of regions here where there's flow velocity compared to regions out here where to first order the air is relatively stationary? Go ahead.
It's lower.
It's lower here than here, right? So these things with Bernoulli and air pressure, I guarantee you're going to find slightly paradoxical at times. And one thing I want to just say as a concluding comment here is don't be tempted to confuse the pressure in the airstream itself when you've got air flowing, fluid flowing more generally. Don't be tempted to confuse the pressure in the airstream itself with what happens if you kind of put your hand, for example, directly in front of where this fluid flow is heading. And so this is true with both airstreams or water streams. It feels like a pressure. And it feels like a pressure that is greater than the pressure that air is pushing on you from the atmosphere. It is a pressure in a sense, but it's actually a kind of series of momentum impulses. And so it's the molecules of the fluid hitting your, in this case, the palm of your hand, that exerts a force overall. And so it feels like there's a high pressure there. All true, but don't confuse that with the local pressure in the flow stream itself compared to the pressure in the part of the flow that's moving either at lower velocity or no velocity at all. Okay? So again, I can guarantee you'll find this a little bit confusing sometimes. Yeah, go ahead.
For the first example of the ball floating, is rotation of the ball necessary for the float?
No. No. It doesn't need to rotate. And I haven't tried to look at this. If you sort of put some markers on there so you could actually see if it's rotating or not, you probably see some rotation, but it certainly isn't required for this to work. Okay, good. So just wanted to make sure that there's slightly surprising demonstrations that you understood what was going on. So let me come back to Bernoulli and just want to say a couple of comments about certain scenarios with solving problems. And most of you are working on finalizing this week's problem set, so hopefully this is going to be helpful. So what's our problem solving strategy? First off, we're always going to be comparing 2 points in the flow stream, or possibly more, but at least 2. And of course, we're applying the equation above at those 2 points. So let's see, a few things to kind of talk about in terms of special cases. These are obvious, but I'm just going to highlight them, and I'm going to talk about a couple of tricks to be aware of. So special cases, the first one is constant height flow. These are just simplifications of a more general Bernoulli equation. And this is exactly a manifestation of what we saw last week with those tubes with water flowing through them. Is dropping out the height-dependent term if I've got constant height flow. And we've already sort of seen examples of this at work, so we've just got our pressure and velocity-dependent terms. We've already talked about that. And then the other special case is if I've got static fluid, which means the velocity-dependent terms drop out, and what I'm left with is, again, something else we've seen already. I've used y here rather than h up there, that's fine. Hopefully you're okay with that changing variables. So this is basically showing us our hydrostatic variation of pressure with height or depth. Okay, so we're recovering what we saw early last week in terms of hydrostatics rather than hydrodynamics. Okay, sometimes we are going to be using our continuity equation. We're simply solving. So, on the surface, pretty straightforward, and in general, most of these Bernoulli type problems are going to be straightforward, but I just want to talk about 2 examples now. One is a little bit generic, the other is rather more specific. So, a couple of example scenarios. These are not full problems, but they're just scenarios. So, first one I'm going to describe as flow from a kind of tank with a small aperture. And this tank will have a certain characteristic, which I'll talk about in just a moment. But maybe it's something that looks like this. So here's a tank full of fluid. And there's a small aperture, in this case towards the base. So presumably once I open this aperture, I've got fluid flowing out of here. Okay. So let's say that the height differential between the surface here and the outlet point is h. And let's say that this is going to be important. This is open to atmosphere. Okay. So there's some color on this. So, open to atmosphere. Let me call this point 1 in the flow and point 2 in the flow. So this is point 1, this is point 2. And I may be, for example, asked to find what is the flow velocity of this fluid as it comes out here. So maybe I'm asked to find what is the flow velocity down here. Alright, so I'm going to use Bernoulli. And there are a couple of subtleties here that, again, are fairly common that I just want to walk through and see if you're okay with this. If this is open to atmosphere, what's the pressure up here? It's atmospheric pressure, right? So this is ambient pressure. So this is atmospheric pressure. If I didn't have this aperture here, and I just had a static volume of fluid, we would expect that the pressure would just increase linearly with depth. Okay, we're back in our hydrostatic situation. Now I'm making this aperture open. I'm kind of pulling out a plug, if you like, and it's starting to flow. What can you say about the pressure in the fluid, kind of in terms of its, let me say, relationship to the ambient pressure out here? That's a slightly cryptic question. But compared to the case where I looked at the pressure in the bulk of the fluid here, and it's static, what can you tell me, roughly speaking, and say this is moving at relatively low velocity, what can you tell me about the ambient pressure outside here? Yeah.
It's also equal to the atmospheric pressure.
It is. So it's actually, once we're kind of outside this aperture, we're back at approximately atmospheric pressure. Okay, so it's in equilibrium again with pressure outside. So that's one sort of approximation you're often going to make when we've got something like this, a tank with a hole in it, we've got fluid flowing out of it. And you're going to be looking, in fact, at the fluid flow once the tank has come out of the aperture. So that's one thing I want you to be aware of. The second thing is you'll often face problems where this is a small aperture and this is a large tank. So keep your eyes open for these kind of phrases. If this is a really large tank, let's say it has a really large surface area, and this is a small aperture, so the volume of fluid flowing through it is modest, what would you say approximately is the velocity of the flow stream up here? Go ahead. It's 0, right. So that's going to be a second approximation you're often going to find in these problems. So for a large tank plus a small aperture, we are often going to make the approximation that that flow speed at the top is close enough to 0 that we can ignore it. Okay? So if I apply Bernoulli to this, what we'll find is that, looking at the top, so I've got P atmospheric plus rho G H. So I'm looking at this height versus this height. There's no velocity term because I'm claiming that to first order the velocity is 0. Then I can say that I can compare this to the second point in the flow stream here, where I'm going to say approximately this is back at atmospheric pressure. And I've got now the velocity dependent term in my right-hand side of the Bernoulli equation. So what this will tell you is that the flow speed out of this aperture is approximately equal to the square root of 2 times g times the height differential. So that's a first common type of approximation problem that you're going to see with Bernoulli. Everyone okay with that? Questions? Yeah.
What if the top was close to the atmosphere?
Okay. So then it's more interesting, right? Because as this thing slowly drops, it's in principle leaving a void behind. So you'd have to worry about what actually is the pressure there. You'd have to worry about basically making the rough approximation that at the top surface, as this thing drops, that you've got 0 pressure there, as opposed to atmospheric pressure. I'm not going to give you a problem like that, but that's how you would solve it. Okay. I kind of feel there was one other thing I wanted to say about this, but I can't remember what it is, so maybe it'll come back. The second thing I want to do is a slightly more specific example of something called a pitot tube. And this is a kind of common problem that combines both fluid dynamics and fluid statics. Anyone know what a pitot tube is? No? Okay. So these are gadgets that have been used in aviation pretty much since people invented airplanes. And they are, next time you get on an airplane, just as you're boarding the plane, take a look down the outside of the airplane. And if you know roughly what to look for, you're going to see examples of these pitot tubes. So they are devices that on commercial airliners are probably about yay big, but they're kind of somewhat tubular shaped. I'm going to give you a sort of schematic cross-section from what one of these things looks like. And it's basically a device to measure velocity of an object with respect to fluid that's moving in. So of course this is very important for airplanes, airliners. You want to know how fast you're flying with respect to the air. So let me try and draw a quick schematic of what this thing looks like. I'm going to blow it up on the vertical scale.